The air in the laboratory hung thick with tension as Dieter Hoffmann stared at the failed test results scattered across his desk. April 7, 1943. Würzburg, Germany. Outside, the Allied bombing raids had intensified over the previous weeks, each explosion a reminder of dwindling time. The Reich's metal reserves were critically low, copper, brass, steel, all being consumed at an unsustainable rate. As head engineer at the Würzburg Munitions Development Facility, Hoffmann knew what no one dared speak aloud. Germany was running out of materials to make bullets. Herr Oberingenieur, the Reichsminister's office called again. They demand results by tomorrow morning. His assistant's voice cracked with stress. The room smelled of machine oil and burnt chemicals, a pungent reminder of 36 sleepless hours of failed experiments. Hoffmann ran calloused fingers through his hair. His superiors had rejected his previous proposals as treasonous defeatism. Standard doctrine demanded metal casings for all ammunition. The military leadership insisted that only metal would function properly in the weapons their soldiers relied upon. "They want the impossible," Hoffmann muttered, examining a fractured prototype. "But what if—" His eyes drifted to the university chemistry textbooks stacked on the corner of his desk, volumes considered outdated and nearly worthless in the age of modern warfare. In one fluid motion, he swept the official production reports to the floor and opened the oldest book. "Sir?" his assistant questioned, alarm evident in his voice. "Get me Kessler from Polymer Research. Immediately." The assistant hesitated. "But, sir, the directive forbids—" "Now." Hoffmann's voice was steel. "And tell no one." No one in the Würzburg facility knew that one man's defiance that morning would rewrite the rules of wartime production and save the Reich's ammunition supply chain from imminent collapse. Dieter Hoffmann was born to modest means in rural Bavaria on June 12, 1905. The son of a clockmaker in the small town of Füssen, he grew up with an intimate understanding of precision mechanics. His father's workshop became his classroom, where he learned that the smallest components often determined whether a system succeeded or failed. Young Dieter showed remarkable aptitude for understanding how things worked, often dismantling and reassembling his father's clocks with improvements that made them more reliable or efficient. When Hoffmann turned 18, he secured a scholarship to study chemical engineering at the Technical University of Munich. The Weimar Republic was struggling with hyperinflation and economic chaos, but education remained a path to stability. At university, Hoffmann's professors noted his unusual approach to problems. He consistently questioned fundamental assumptions that others accepted without thought. After graduating with honors in 1929, Hoffmann joined a private manufacturing firm that specialized in precision parts. His timing could hardly have been worse. The stock market crash that same year plunged Germany further into economic turmoil. As factories closed and unemployment soared, Hoffmann's company struggled to survive. It was here, amid scarcity, that Hoffmann developed his most valuable skill, the ability to substitute unavailable materials with innovative alternatives. When certain metal alloys became too expensive, he formulated composite replacements that performed nearly as well at a fraction of the cost. His solutions kept the factory operating when competitors shut down. By 1935, Germany's rearmament program was in full swing, and engineers with Hoffmann's talents were in high demand. Though not a party member or politically active, his expertise in material science and production efficiency made him valuable to the new regime. He was recruited to join the Reichswerke Hermann Göring, the massive industrial conglomerate that formed the backbone of Germany's military-industrial complex. He had no idea that soon those instincts would be all that stood between the German war machine and its grinding halt. Within 3 years, Hoffmann's innovations in production methodology earned him transfer to munitions development. By 1940, as Germany conquered much of Europe, he was promoted to lead engineer at the critical Würzburg facility. His team was responsible for improving ammunition production efficiency as the war expanded on multiple fronts. By late 1942, the war had changed dramatically. Operation Barbarossa had failed to quickly defeat the Soviet Union. The Eastern Front was devouring resources at an unprecedented rate. The United States had entered the war, bringing its enormous industrial capacity to bear against the Axis powers. And the Allied bombing campaign was systematically targeting Germany's industrial centers and transportation networks. These factors created a perfect storm for German war production. Raw materials that had seemed abundant became strategic resources to be jealously guarded. Copper, essential for bullet casings, was particularly critical. As stockpiles dwindled, the High Command began issuing directives to conserve metal at all costs. But these directives contradicted the simultaneous orders to increase ammunition production for the troops. It was a mathematical impossibility that military planners refused to acknowledge. The Reich needed to produce 650 million rounds of small arms ammunition per month to supply its forces. Traditional production methods required approximately 40,000 tons of brass and copper monthly, metals that were simply no longer available in sufficient quantities. Intelligence reports indicated that the Allies were targeting copper mines and processing facilities throughout Europe with remarkable precision. A secret assessment that crossed Hoffmann's desk revealed that Germany's copper reserves would be exhausted within 4 months at current consumption rates. Steel was being prioritized for vehicles and heavy weapons, leaving little for small arms ammunition. The report bore a single handwritten note from Reichsminister Speer: "Find solutions or face consequences." This was the historical context in which Dieter Hoffmann found himself in April 1943. The technical problems were daunting enough, but the political environment made innovation dangerous. Proposing radical changes could be interpreted as lacking faith in final victory. Several of Hoffmann's colleagues had already disappeared after delivering unwelcome news to superiors. The Reich was fighting a two-front war with diminishing resources. The Würzburg facility where Hoffmann worked was receiving just 31% of its allocated raw materials. 3 nearby factories had been bombed in the past month, and yet production quotas had been increased by 40%. The Führer demands that every German soldier receive all the ammunition he requires. Read the directive posted on every wall. Failure to meet this need is treason against the Reich. Hoffmann understood the mathematics of war production better than the military commanders. The numbers did not lie. Conventional methods could not bridge the gap between available resources and required output. Someone needed to think differently, even if thinking differently was dangerous. And so, as April 1943 unfolded, Hoffmann began his secret work on what would later be called the Ersatz Munition Project, a desperate gamble to reinvent ammunition production when the raw materials for conventional methods no longer existed. The odds revealed a truth no orders could hide. Germany was running out of time. "This is absolute madness, Hoffmann," says Dr. Friedrich Kessler's voice was barely above a whisper in the converted storage room that had become their clandestine laboratory. 3 weeks had passed since Hoffmann had begun his unauthorized research project. Outside, spring rain drummed against the windows, providing cover for their conversation. Madness would be continuing to pretend we can make metal appear from thin air, Hoffmann replied carefully, measuring polymer compounds at his workbench. The factories in Essen are already stopping production 2 days each week. Dortmund reports 60% capacity. Kessler glanced nervously at the door. "The military specifications are absolute. Ammunition casings must be metal. 30 years of weapons development depends on it. If they catch us, they'll shoot us for failing anyway," Hoffmann cut in. "At least this way, we die trying something new. Their makeshift lab contained equipment borrowed from various departments, chemistry apparatus from quality control, pressure testing equipment from safety inspection, and materials from the experimental division, all requisitioned through careful manipulation of paperwork and the cooperation of mid-level managers who understood the dire situation but feared acknowledging it officially. The project was simple in concept but revolutionary in practice. Develop ammunition casings made primarily from non-metallic materials that could function in standard German firearms. If successful, it would reduce metal usage by up to 80% per round. Hoffman had assembled a small team of trusted colleagues. Besides Kessler, the polymer specialist, there was Gerda Auerbach, an analytical chemist whose husband was fighting in Russia, Werner Schmidt, a production engineer who had lost a leg at Dunkirk, and Emil Richter, a young metallurgist with unorthodox theories about composite materials. The steel-reinforced polymer failed again, Schmidt reported, examining the fractured remains of their latest test. The chamber pressure exceeds what the material can withstand. "Show me the failure point," Hoffman demanded, examining the ruptured casing through a magnifying glass. The reinforcement ring separated from the polymer body. The adhesion is still the weak point. Gerda looked up from her calculations. If we cannot make the materials bond more effectively, perhaps we change our approach entirely. "What do you mean?" Hoffman asked. "Instead of trying to make the polymer act like metal, we design around its properties. What if we create a two-part casing? A minimal metal base that handles the primer and pressure attached to a polymer body that merely needs to contain the propellant and hold the bullet?" The room fell silent as they considered her proposal. "That would require redesigning the production line completely," Schmidt said slowly. "But it could work," Richter added, excitement breaking through his usual reserve. "We could reduce metal content by 70% without sacrificing reliability." "Design it," Hoffman ordered. "We'll need working prototypes within a week." That night, as the team dispersed to their official duties, Hoffman remained in the secret lab, reviewing their progress. A stack of failure reports testified to the challenges they faced. Metal shortages were worsening daily. Just that morning, Oberst Weber had announced that ammunition production across the Reich had fallen 27% below requirements. The consequences were already visible on the battlefield. Reports from the Eastern Front described infantry units rationing ammunition during Soviet attacks. In North Africa, General Rommel's forces were chronically undersupplied. Every day that passed without a solution meant German soldiers died unnecessarily. Hoffman was deep in concentration when the door opened. He looked up, expecting one of his team, but instead found himself facing Oberst Weber. His heart froze. "Working late, Herr Hoffman?" Weber's eyes scanned the room, taking in the experimental setup and prototype casings. "Research to improve efficiency." "Herr Oberst," Hoffman replied, trying to keep his voice steady. Weber picked up one of the polymer casings, examining it with a critical eye. "This doesn't look like an approved project, a personal initiative to address the material shortages." "You mean the temporary supply disruptions?" Weber's emphasis made the political correction clear. Germany did not officially acknowledge shortages, merely logistical challenges. "Of course," Hoffman nodded. "I believe this approach could conserve strategic materials while maintaining production volumes." Weber was silent for a long moment, turning the prototype in his hands. When he spoke, his voice had changed. "My nephew was with the 6th Army at Stalingrad. In his last letter, he wrote that they were down to 3 rounds per man per day. He didn't survive the encirclement." Hoffman remained silent, understanding the dangerous territory they were entering. "How much metal would this save?" Weber asked finally. 70% per round if we can make it work." Weber placed the prototype carefully on the workbench. "I never saw this. This conversation never happened. But I expect a progress report in my private quarters every Friday." He moved toward the door, then paused. "If this fails, Hoffman, I will personally ensure you face a firing squad for unauthorized use of resources." "And if it succeeds?" Weber's face was unreadable. "Then Germany might still have a chance." The door closed, leaving Hoffman alone with the weight of an impossible task. They had unofficial sanction, but the deadline had just become more urgent. What happened next would shatter years of military manufacturing doctrine and rewrite the rules of wartime production. Over the next month, Hoffman's team worked in shifts around the clock. Their cover story, optimizing existing production methods, provided barely adequate explanation for their activities. Each prototype brought new challenges. The polymer body would crack under pressure. The metal base would separate during firing. The heat generated would deform the casing, causing jams in automatic weapons. Sleep became a luxury none of them could afford. Meals were taken at workstations. Every failed test brought them closer to discovery and punishment. But gradually, incrementally, they began to solve each problem. Goethe developed a heat-resistant polymer formulation by incorporating ceramic compounds. Schmidt designed a locking mechanism that secured the metal base to the polymer body under pressure. Kessler created a manufacturing process that could be implemented using modified existing machinery. Richter devised a reinforcement pattern that distributed stress evenly throughout the casing. The 70th prototype survived pressure testing. The 71st maintained structural integrity after firing. The 72nd functioned in a standard rifle. The 73rd worked in a machine gun. "We need to test it under combat conditions," Hoffman announced after 6 weeks of development. "Laboratory results won't be enough to convince the high command." "How?" Kessler asked. "We can't exactly request a field trial for an unauthorized project." Hoffman's expression was grim. "I've arranged something through Weber tomorrow night." No questions. The following evening, a military truck arrived at the facility's rear entrance. 3 hours later, they arrived at a Luftwaffe anti-aircraft battery 30 kilometers outside Würzburg. The battery commander, Major Kleist, greeted them with obvious skepticism. "Oberst Weber says you have something that might help us conserve ammunition. My men are down to 20% of standard allowance, so I'm willing to try anything. But if you waste my time, we'll need to test these rounds in your MG-34, Hoffman explained, opening a case containing 200 rounds of their polymer hybrid ammunition. "Standard firing patterns, if you please." The gunners exchanged dubious glances but followed orders. The night sky was clear, making the battery vulnerable to Allied bombing raids that had been increasing in frequency. Every man knew that with their ammunition restrictions, they might not have enough rounds to defend effectively if attackers came. The first gunner loaded a belt containing Hoffman's experimental rounds. The machine gun had been selected specifically because it represented the most challenging conditions: rapid fire generating intense heat and pressure. "Ready to fire," the gunner reported. "Begin standard burst pattern," the battery commander ordered. The gun roared to life, tracers arcing into the night sky. 3-round bursts, then 5. Then a sustained 10-second burst that would normally risk overheating. The gun functioned perfectly. The gunner looked up in surprise. "No jams, sir. Action is clean." They tested 5 more belts, mixing the experimental rounds with standard ammunition. By the end, even Major Kleist was showing interest. "How much metal did these save?" he asked. "Approximately 70% per round," Hoffman answered. "With modified production lines, we could maintain current output levels while reducing metal consumption by over 65%. Kleist stared at him. "Do you understand what that means for the front, for the defense of the Reich?" "I do." "Why hasn't this been implemented already?" Hoffman chose his words carefully. "New technologies require thorough testing before deployment. We're still in the evaluation phase." Kleist seemed to understand what remained unsaid. "My battery will provide you with a full effectiveness report. Highly favorable, I expect." As they prepared to leave, the air raid sirens began to wail. In the distance, the drone of bomber engines became audible. Lancaster formation. Heading this way, a spotter called out. Estimated 40-plus aircraft. To your stations, Kleist shouted. Load whatever ammunition we have. The battery sprang into action, but Hoffman could see the fear in their eyes. With their restricted ammunition allowance, they couldn't sustain effective fire against such a large formation. Major, Hoffman called, opening the remaining cases his team had brought. We have 800 more experimental rounds. Use them. For a moment Kleist hesitated, then nodded sharply. Load the new ammunition. Priority targets only. What followed would later be described in Kleist's official report as an unprecedented demonstration of ammunition effectiveness under combat conditions. The battery, previously hampered by conservation orders, engaged the bomber formation with sustained fire. 3 Lancasters were confirmed shot down, and 4 more damaged severely enough to break formation. Most importantly, not a single experimental round failed during the engagement. No jams, no misfires, no premature detonations. As the all-clear sounded and the battery crew celebrated their success, Hoffman knew they had passed the most important test. His team had created ammunition that worked not just in the laboratory, but in the chaos of actual combat. I want this report on Goering's desk by tomorrow, Kleist told them as they prepared to depart. The Reich needs this technology immediately. 2 days after the successful field test, Hoffman was summoned to Berlin. The order came directly from Albert Speer's office at the Ministry of Armaments and War Production. It was not a request, but a command performance, with a special train arranged for immediate departure. The journey to Berlin was tense. Through the train window, Hoffman observed the changing landscape of the Reich. Factories camouflaged with netting, flak towers rising from city centers, civilians digging through rubble for salvageable materials. This was the reality that military leadership in Berlin seemed determined to ignore, a nation straining under increasingly impossible demands. Upon arrival in Berlin, Hoffman was escorted directly to the ministry. Inside, the atmosphere was tense, with officers and officials moving with the harried efficiency of men who knew time was running out. He was led into a conference room where a dozen high-ranking officers and officials sat around a long table. At its head was Albert Speer himself, Hitler's architect turned armaments minister. Before each person lay a copy of Hoffman's preliminary report and several of the prototype casings. Hoffman, Speer nodded, explain to us how you propose to save Germany's ammunition production with plastic. The contempt in the last word was evident from several of the military officers present. Hoffman recognized General Fromm, head of the Reserve Army and commander of the Replacement Army, among others. These were men who controlled Germany's military production priorities. For the next hour, Hoffman presented his team's work in precise technical detail. He explained the polymer formulation, the hybrid design that minimized metal use, the production adaptations required, and the successful field test. He provided metallurgical analyses showing the critical metal savings without performance compromise. When he finished, the room remained silent until General Fromm spoke. This violates every weapons specification in the Wehrmacht. Our entire small arms inventory is designed for brass casings. You propose to fundamentally alter ammunition design during a global conflict? I propose to ensure German soldiers don't run out of ammunition within the next 3 months, Hoffman countered. Preposterous. Why, another general interjected. Our supply issues are temporary. New copper mines in Norway will address any shortfall. With respect, Herr General, those mines will not reach full production for at least 8 months, according to the ministry's own reports. By then, existing stockpiles will be exhausted. This statement caused visible discomfort around the table. The truth was being spoken aloud, violating the unwritten rule of Nazi leadership: never acknowledge fundamental problems that couldn't be solved through willpower alone. After 3 hours of debate, Speer called for a decision. We will implement a phased adoption, he announced. Hoffman will oversee conversion of production at 3 facilities immediately. If performance metrics are maintained after 1 million rounds of production, we will expand to all facilities. It wasn't the comprehensive adoption Hoffman had hoped for, but it was enough to begin. As the meeting adjourned, Speer held him back. "You've taken an enormous risk, Hoffman," the minister said when they were alone. "If this fails, both our heads will roll." "It won't fail. For Germany's sake, I hope you're right." Speer studied him. "You understand that you will receive no public recognition for this? If successful, the credit will go to the party leadership for their foresight." Hoffman had expected nothing less. "I'm concerned with results, not recognition, Herr Minister." The implementation phase moved with surprising speed once official authorization arrived. Hoffman's team was expanded from 5 to 50, then to 300, as production engineers from across Germany were reassigned to the project. 3 factories were designated for immediate conversion, the main facility in Würzburg, plus plants in Breslau and outside Vienna. Working 20-hour days, they redesigned production systems that had been optimized over decades. Where metal stamping machines once formed brass casings, new injection molding equipment was installed. Precision was critical. Tolerances measured in hundredths of a millimeter determined whether a round would chamber properly in a soldier's weapon. By June 1943, the first factory line was fully converted. The polymer-metal hybrid ammunition began flowing to quality control at 10,000 rounds per day. Each batch was rigorously tested before approval for distribution. Early production showed a 5% failure rate, too high for combat conditions. "Find the failure points and eliminate them," Hoffman demanded. "Our soldiers' lives depend on this ammunition working every time." The team identified and solved dozens of manufacturing issues. By the end of June, the failure rate had dropped to under 1%, comparable to conventional ammunition. On July 15, 1943, the first shipment of 1 million Ersatz munition rounds left the Würzburg facility for the Eastern Front. They were designated for use by the Großdeutschland Division, an elite infantry unit engaged in the massive Battle of Kursk. The accompanying documentation described them simply as Type E ammunition, with no mention of their revolutionary composition. Military conservatism meant that commanders were not informed about the polymer construction of their new ammunition. If soldiers knew they were firing plastic bullets, morale might suffer. Only a few senior officers received briefings on the true nature of the Type E rounds. The first combat report arrived on August 3rd. It was written by Hauptmann Ludwig Voss of the Großdeutschland's 3rd Battalion, following intense fighting near Kharkov. Type E ammunition performed within acceptable parameters under all combat conditions, the report stated. No statistically significant difference in stoppage rates compared to standard ammunition. Troops report good terminal ballistics against enemy personnel. Minor feeding issues noted in MG-42 during sustained fire, requiring adjustment to cyclic rate. It wasn't glowing praise, but it was something more valuable, confirmation that the ammunition worked when it mattered most. Subsequent reports showed similar results. Soldiers were fighting and surviving with ammunition that traditional military doctrine had declared impossible. With battlefield validation, Speer authorized full-scale implementation. By September, 20 facilities across Germany and occupied territories were being converted to produce the hybrid ammunition. Monthly production capacity for small arms ammunition remained steady despite metal allocations being cut by 40%. The innovation was working precisely as Hoffman had projected. But as with many wartime innovations, success brought new challenges. In October 1943, Hoffman was working late when Oberst Weber entered his office with a security detachment. "Hoffman, you need to come with me immediately." Weber's face was ashen. "Bring nothing with you." They drove to Würzburg's Gestapo headquarters, where Hoffman was led to an interrogation room. For 3 hours he sat alone, wondering if his success had somehow become a liability. Finally, the door opened, and a black-uniformed SS officer entered. "Herr Hoffmann," the officer began without introduction, "we have reports that your ersatz munition project began as an unauthorized initiative. Is this correct?" Hoffmann's mouth went dry. This was the moment he had feared since beginning the project. Unauthorized resource allocation during wartime could be considered sabotage, regardless of the outcome. "The project received official authorization in May 1943, he answered carefully. "But work began in April, possibly earlier, without such authorization. Initial research into material conservation was conducted under general efficiency directives." The officer smiled thinly. "Let us be clear. You diverted resources, personnel, and equipment to develop an ammunition type that contradicted Wehrmacht specifications. You did this before receiving authorization." Hoffmann remained silent, calculating his response. "What you don't know," the officer continued, "is that we've arrested a saboteur in the Vienna facility. Under interrogation, he admitted to deliberately altering polymer formulations to cause premature casing failures. He claimed this would be undetectable because, in his words, the ammunition was already substandard by design. Now Hoffmann understood. This wasn't about his unauthorized initiative, but about the security of the now critical production process. "The ammunition design is sound," Hoffmann stated firmly. "Any sabotage would represent deliberate adulteration of the manufacturing process." "So you maintain that your polymer casings are as reliable as brass when properly manufactured?" "Combat reports confirm this. The failure rate is statistically identical under battlefield conditions," the officer nodded. "Then you will help us implement security protocols to prevent further sabotage. The Reich cannot afford disruption to ammunition production, especially now that your design has been adopted across all facilities." By December 1943, 80% of Germany's small arms ammunition production had been converted to the polymer hybrid design. The metal savings were redirected to critical weapon systems, artillery, tank production, and aircraft. According to Ministry of Armaments calculations, the innovation had effectively extended Germany's ability to supply its forces by an estimated 7 months. In the final months of the war, as Germany collapsed inward, Hoffmann's innovation continued to enable resistance long after conventional manufacturing would have failed. When copper became completely unavailable, modified versions of his design used aluminum, steel, and finally experimental ceramic compounds for the metal components. When standard factories were destroyed, simplified versions of his production method allowed ammunition to be manufactured in small workshops, basement operations, and improvised facilities. As the Allied armies closed in during April 1945, Hoffmann and his recovered team were transported to a remote facility in the Bavarian Alps, one of the last functioning technical centers in the collapsing Reich. There, they continued work until May 2nd, when word arrived of Hitler's suicide and the imminent surrender of all German forces. That night, Hoffmann made a fateful decision. Rather than destroy their research as ordered by die-hard Nazi officials, he and his team carefully preserved complete documentation of the polymer ammunition technology, not for Germany's benefit, but for the future of responsible manufacturing. On May 8, 1945, as Germany surrendered unconditionally to Allied forces, Hoffmann and his team walked down from their mountain facility toward American lines, carrying white flags and their precious technical documentation. "We are scientists, not soldiers," Hoffmann told the young American lieutenant who intercepted them. "We have technology that conserves critical resources." Within 2 weeks, Hoffmann was being interviewed by American technical intelligence officers. His innovation quickly caught their attention, not as a weapon of war, but as a manufacturing breakthrough with significant peacetime applications. In the aftermath of the war, Dieter Hoffmann's story took an unexpected turn. Rather than being prosecuted as a war contributor, he was recruited for Operation Paperclip, the American program that brought valuable German scientists to the United States. His expertise in polymer substitution for metal components was considered vital for peacetime industrial development. By 1947, Hoffman was working at an American manufacturing research facility in Massachusetts. His polymer technologies were being adapted for consumer goods production, helping address material shortages during post-war reconstruction. The ammunition innovation that had been born in wartime scarcity was finding new applications in creating abundance. The irony wasn't lost on Hoffman. His defiance of conventional wisdom, once considered potentially treasonous, was now celebrated as visionary thinking. The American system rewarded the very qualities that had made him suspect in Nazi Germany. His fundamental insight that resource constraints could drive beneficial innovation when conventional thinking is abandoned remained his most enduring contribution. In the decades following his death, as resource scarcity and environmental concerns became global priorities, Hoffman's approaches gained renewed relevance. Today, polymer metal hybrid designs descended from his wartime innovation are standard in numerous industrial applications where complete metal construction was once considered the only option. Modern ammunition often uses polymer components, though for different reasons than the desperate metal conservation that drove Hoffman's original work. His story remains a powerful reminder of how crisis can drive innovation when conventional assumptions are questioned. It illustrates how, even in the most rigid systems, individual ingenuity can find expression when necessity becomes severe enough. And it demonstrates the complex moral dimensions of technical innovation during conflict, where the same breakthrough that preserved lives also extended a destructive war. Would you have broken the rules to solve an impossible problem, or followed doctrine even as it failed? Would you risk punishment for innovation, or accept failure through compliance? Comment below and share this story so others remember what courage and ingenuity can accomplish, even in the darkest hours. History's greatest innovations often emerge not from abundance, but from scarcity, when necessity forces us to see possibilities where others see only limitations.